All right, here is a set of example problems for you for using this three types of students t-tests. And I want to start with this problem number one, looking at annual lightning strike deaths. And it asks you from this set of data to find the mean and the 99% confidence interval. We're just doing this quick example of finding a confidence interval to point out that everything we learned about confidence intervals using little z is easily translated to little t. So the first thing to do, tackling any problem, is going to write down all the information that you are going to need. So the first thing we want to look at is we have a sample. There's a number of deaths, which is going to be our x variable for each of these years. There's a total of 10 observations. So we'll start by writing down our sample size, little n equals 10. And we know we're going to need to find the mean, right? So x bar. And since we've already worked on this in class before, and you can even use Excel to find it, I'll just give that to you for the purposes of this problem. And calculating the mean is going to be 37 deaths per year in this time interval. It's tempting when you calculate this value to use some decimal places, but the data don't have any, so we'll round it off to no decimal places. Likewise, we're going to need the standard deviation. So go ahead and use Excel to calculate that. It comes out to 9. Again, rounding off. All right, so we found the mean. Now we want to find a confidence interval around it. In order to write a confidence interval, we're going to use the equation x bar plus or minus. Remember, we have two n's to our interval. And we're going to just substitute t star in for z star times s over root n, right? Our t star is going to depend on what we set for our confidence interval. So for a 99% confidence interval, we're going to go to the to the t table. All right, so if you haven't looked at this yet, it's really easy to use for confidence intervals because what it gives us is the critical values. Those are the T stars. And the confidence levels are here right across the top. So all we need to do is go across the top and find the column for 99%. Now we need to know what row to go to. And the rows are determined by something called degrees of freedom. Now, degrees of freedom are going to be little n minus 1 for the t-test. And our n is 10, so our degrees of freedom is going to be 9. I should have written that down before we started. All right, but here's our 9. We're going to go across to our 99%, and that tells us our t star is 3.25. All right, so what I should have written down already was our degrees of freedom, and that's going to be little n minus 1. So 10 minus 1 equals 9. All right, so then we just need to plug in the little s and the root n and our mean. So 37 plus or minus 3.25 times s over root 10. All right, and to calculate this, we just divide 9 by root 10, which is 3.16. So 9 divided by 3.16 times, make sure you get that quantity in your calculator first, times 3.25. And that's gonna simplify to 37 plus or minus 9.25. All right, if we actually do the addition and subtraction, so this is our um, standard error of the mean. We actually have to add it to the mean, subtract it from the mean to give us our endpoints for our confidence intervals. So remember when I ask you for a confidence interval, that means the left-hand end of it and the right-hand end of it. We're going to get the left end of it by taking 37 minus 9.25, and that's going to give us 27. Now, we started out with units that were whole numbers. Because we introduced this T star, we can use numbers after the decimal, but I'll probably just round it down to 1. So we're going to get 27.7. So that comes from 37 minus 9.25 and just round it to 1 decimal. Now I'm going to do 37 plus 9.25. That gives me 46.2. All right, so if we wanted to make sure that 99% of the time we took a sample and we built an interval around it, that we captured the true mean of annual lightning strike deaths between 2000 and 2009. That would be between 27.7 and 46.2. Right. That is a complete answer to question 1. For the next question, question 2, it gives us the information that the mean of lightning strike deaths from 1980 to 1989, that is in the 1980s, was 72.6, and asks us to investigate the research question: has the number of deaths decreased in the 2000s compared to the 1980s? And we're going to use the same sample that we used in problem 1. So I started by writing down my 2000s and just recopying the information down here to make sure that I have it all straight and squared away, because I know I'm going to need it to do this hypothesis test. All right, so we have this sample and we're being asked to compare it to a single specific value. All right, so we're going to use the one sample t-test, and we want to ask a question or test a hypothesis that this mean is equal to that mean. Right, so we want to designate that mean that we're using as our comparison. That is going to be our mu sub 0, the mean that's in our null hypothesis. All right, we want to ask, from our sample, does our mean x equal this hypothesis? So we've got our mu sub 0, and in order to do our hypothesis test, we need to set our alpha level first. So let's set a reasonably stringent alpha level. And I'm either going to give you this, or you can always use an alpha of 0.01 or 0.05 if I don't give you. All right. So we want to start by writing our hypotheses. We're always going to have a hypothesis, a null and an alternate hypothesis. And we're going to always say the true mean, mu. And in this case, it's going to be equal to this null hypothesis mean, that the number that we want to compare our sample to. of 72.6. All right, now we're going to have mu does not equal is less than or greater than 72.6. So when we're writing our alternate hypothesis, we need to take into account what the research question is asking or what we're expecting to see, right? And so this question is asking, has the number of deaths decreased, right? Is our mean thus going to be less than 72.6? Now, when we look at it, then we can compare and we say, well, 37 is less than 72.6, but there is some variation in our sample, and that's why we're doing a hypothesis test to see if it's smaller enough that it's statistically significant. All right, in order to evaluate our hypothesis, we first need to find our test statistic. And for little t is our test statistic for this test. And you want to find on your equation list our one sample t-test equation, which is going to be x bar minus mu 0. And we only have one sample here, so that's going to be divided by uh, standard deviation divided by root n. All right, so to calculate our t, we're just going to substitute in this equation. Our x bar is 37. Now it's important to always write this equation in this order with the minus sign in the middle. So we're doing x bar minus mu sub 0. So that's going to be 37 minus 72.6. It's going to give us a negative number, and that's what we want. All right, we're going to substitute in 9 over root 10. And making that calculation, you should get negative 12.4. Right, that's a pretty big value for a t. Make sure you calculate it using your own calculator and that it matches this value. All right, so now we need to find, we got our t, now we need to find little p. All right, how are we going to do that? We're going to go to the t distribution table. So keeping in mind our degrees of freedom is 9, we want to find the t that's associated with this value that we found. All right, so let's go to the t table. All right, so now we're not going to start by looking at the confidence level. We're just going to go straight to the row of our table for our degrees of freedom. Now we have this calculated value of t. Now the values of t in our table are all positive, but we're going to assume that they are acting or they're standing in for either positive or negative values of our t. So we can actually kind of ignore this minus sign and just use this the values in the table. All right, so if we go across, we're looking at degrees of freedom of 9, 0.7, 0.8. Wow, those are really small. We're going across, going across, going across. And we get to the end of our table, 4.781. That is still less than um, our value of t. So all we can say is that our value of t is larger than this value that's in the table. So we're going to write down 4.1, and that's going to be less than our value of 12. All right, so this is our t calculated. And this is the last t we could find in the table. All right, to find the p-value, we're going to go down to the bottom of the table. See that a little better. And we can see over here one-sided p, two-sided p. Now, how we wrote our alternate hypothesis is going to tell us if we want a one-sided p-value or a two-sided p-value. We used a less than, be the same if we used a greater than sign. So this is a one-tail hypothesis, all right? So we have to use what's asked for in the research question. We write that into our alternate hypothesis. And then when we're using the table, we know it's a one-sided p because of how we wrote our alternate hypothesis. All right. So what I have here is 0.0005. Yep, that's 0.0005. Oh my. All right, so our p-value, now let's look at our p-values. They're getting smaller as we go towards the right. So our p-value is actually going to be over here. All right, so, oops. And then when we're looking at which direction the p-values go, because our value of t is bigger, it actually means that our value of p is going to be smaller. So our p is going to be less than. So between our values of t and our value of p, we're going to flip the direction of the greater than less than sign. So our p is going to be less than 0.0005. All right, very small. Is our p, this is our next step, is p less than alpha? All right, our p is less than our alpha. Is p less than alpha? Yes. All right, if all right, so here I wrote that down right over here. Our question is p less than alpha. Here's our alpha. Here's our p. It's less than alpha. Yes. All right, so I'm going to go to the next page of my notebook because we still have to write our conclusion. All right, what do we do with our null hypothesis if is less than alpha? We reject the null hypothesis. All right, what was our null hypothesis? That our mu was equal to 72.6. If we reject our null, we accept our alternate. So we're going to say that this is our number of lightning deaths from the 2000s, right? We reject the null, which is that mu equals 72.6. So we accept the alternate. All right, so you don't have to write down these two steps. I'm just making sure you're understanding all the steps. So what we're going to write as our final answer, our result of our experiment, is death by lightning strike, or deaths by lightning strikes in 2000s are statistically significantly less than, fewer than in the 1980s. All right. How much less are they? And if you were writing up the results of your experiment or you were talking about how big the difference was, you could actually put in some actual values here. But this is the most important part. All right, we've got our statistically significantly less. All right. And it's fun to think about why this might be true. Um, so maybe there's more public service announcements about avoiding lightning strikes. Maybe there's better health care, better access to ambulances and 911 service so people don't die if they are struck by lightning. Um, Maybe there's less lightning. We don't know any of those things. We just know the result of our hypothesis test. For question 3, we have heart rate measurements that students took from resting, then they did an intervention, they did some exercise, and then we have each student, same individual, a second measurement. So this is the appropriate type of situation for a paired t-test. We have one set of individuals that we measured twice, and the difference between those two measurements is going to tell us something about what happened due to that intervention we did in between those two measurements. All right, so I wrote out the data for this problem. So these are the heart rates from the first person, their resting heart rate, their post-exercise heart rate. We have a pair of observations for each person. If for some reason one of them had forgotten to write down their first measurement or something, and we only had one of the two measurements, we have to throw that data point out. We have to have both in order to include the individual. So I wrote down a few things that we're going to need that we can do right off the bat. We've got 8 total students. That means our little n sample size is 8. We know we're going to need a degrees of freedom. So degrees of freedom is going to be 8 minus 1 or 7. Now, once we get this little n and this degrees of freedom, sometimes we make a mental mistake and we use the wrong one. Like, for example, if you were working and you were putting numbers into this equation, which is the one that we need for our paired t test statistic. If you were thinking little n, but you happen to glance at this degrees of freedom 7 and put that in, you'd get a slightly wrong answer. So it helps to write down the variable and the value so that when you are substituting into the equation, you can go back and make sure you have the right number. All right. So what we actually want to find the mean and standard deviation of are the differences between these two observations. So it's a little confusing at first when you're staring at this equation and you're staring at the data, because first you have to do a calculation step, right? So we are going to, and I'm writing it in a different color just to draw your attention to the fact that it's an extra step. You have to remember that this is how you're going to get that X bar diff and the S diff. All right, now we're just going to subtract one of the observations from the other. It doesn't really matter which one we do. The values are all going to, well, in this example, they're all going to be either positive or negative, but you just need to make sure you're subtracting the same way for all the observations and that you include plus and minus signs in case there are different directions that your numbers are going. So we're just going to subtract and get the difference between these two measurements. These are easy to do by eyeball. So 28, 38, 54, 48, 720, 17, Right, so once we have these differences, then we can use Excel or we can use our calculator. We're going to use these differences in order to calculate our X bar diff and our little s diff. All right, so I used Excel to calculate these and I got 36 for X bar diff and 24 for S diff. All right, notice that there's a huge range in the amount of difference between the first and the second heart rate. There's actually quite a broad range in the resting heart rates from one individual to another. All right, so in order to test our hypothesis, we need to have a null and an alternate like we always do. So we'll start there. And we can write the null and alternate hypotheses for um, the paired test two different ways. Whichever one makes more sense to you is fine, but I'll show you both. So we're going to have a null and an alternate. And one way to write them is the mu diff, the true difference between our two measurements is mean of these differences is 0. There's no difference between our measurements. And this question is asking us, is the heart rate after exercise different than heart rate before exercise? So this different is telling us we're doing a two-tailed hypothesis test, right? And we're just finding out, is our mu diff, is it equal to 0 or is it not equal to 0? All right, so the other way we can write these hypotheses, and again, whichever way you prefer is fine. We can say that the before values are equal to the after values, right? So if the values before our heart rate at rest are equal to the heart rate post exercise P. All right, now if they are equal and we subtract one from the other and get the mu diff is 0. So these are really saying the same thing. It's just more of how you think about it. I personally like this one because it's a little easier if you have less than or greater than. If you have a one-tail alternate hypothesis, it's easier to figure out how to write this one. All right, and so we have a two-tailed alternate because we have different in our research question. And so we're just going to say mu r, it's either equal to or it's not equal to mu p. All right, so this is going to be a two-tailed test. We're going to use an alpha of 0.05. And if you have, if I don't give you one, then you can always use 0.05 or 0.01. And we need to calculate our test statistic. So we're going to take little t equals, we're going to substitute in our X bar diff. So we're going to get 36 over our little s diff, right? Our standard deviation of the differences. So that's going to be 24 divided by root of our sample size, right? 8. And if you calculate that out, again, be careful making sure you get this division done or you divide the 36 by the result. You should get little t equals 4.18. All right, what does that mean? All right, we've got to go to the t distribution table. All right, so once we calculate our test statistic little t, we're going to use little t to find p. All right, let's look at that distribution. Where'd it go? All right, so looking at our t distribution, we're looking for our value of t, 4.18, and we have 7 degrees of freedom. So we'll go to the 7 and we'll go across. We're looking for 4.18 to do 4.029, 4.785. Okay, it's actually in between these. Now, we could use uh, um, software or uh, an online calculator to find our exact value, but we want to use, I want you to use the table. So here's what we're going to do. We don't have an exact value of t in our table. So we're going to write down the values of t that our value of t is in between. So it's in between 4.029 and 4.785. And now when we go to those columns, so we're going to scroll down. All right, and we're looking for the two-sided key, and the one associated with 4.09 is 0.005, and the one associated with 4.785 is 0.002. All right, so our P is going to be, right, so our T was in between these two numbers. So our P is going to be in between the numbers that we find associated with those values of T. All right, however, T's get bigger as we go to the right, but P's get smaller as we go to the right on the table. So as we go from the T to the P, we're going to flip the greater than, less than signs. All right, so this is our p-value. We can say is that it's in between these two values, right? We've got an alpha of 0.05. The next step is to compare, is p less than alpha? All right, now our p is less than 0.005. All right, that means it's also less than 0.05. Yes, our p is less than our alpha. That means we're gonna reject the null. If we reject the null, that the mean of the rest and the post-exercise heart rates are the same, then we accept the alternate that they are different. And so that allows us to say that the heart rate after exercise is statistically significantly different than resting heart rate. Okay, if we examine the data, we do see that all of the heart rates after exercise are higher than the resting ones. Now, why we want to use a paired test here is because if we look at people's resting heart rates, there's quite a wide range here. So people have different amounts of coffee they've drank, different aerobic capacity and fitness they have. They may be taking a medication. People are going to have different resting heart rates. So we have so much variation between individuals that we actually um, theoretically get a better measurement of the impact of this exercise when we look at this before and after situation. And we have a lot of human um, uh, health metrics that we use these sort of before and after measurements because individual humans have so many different variables affecting them that it's hard to find a group that we don't see this kind of large variation between individuals. All right. And we still have a lot of variation in this amount of difference, and that's going to depend on people's, amount of exercise they do normally, and how hard they were trying when they did those, when they did the walking in place. All right. That is the end of problem 3. Here is our last question, number 4, and it asks, does brewery waste outfall affect the fish downstream? All right, so whenever we have any kind of factory that's right on a river, often they discharge or dump um, water, sewage out, like waste from their manufacturing processes directly into bodies of water, not as much as they used to. But if this question is confusing for you, here's a little diagram. We've got a river and it's flowing this direction. We have our brewery here with its outfall pipe going out into the water. And we have sampled some fish. Those little X's represent fish that are upstream, right? So as the water flows, it should be carrying all the waste downstream. So these fish that are upstream shouldn't be exposed to as much or any, depending on the rate of flow, how much, and assuming the fish stay up here. Downstream is below on the river's elevation, so that they should be getting exposed to whatever's coming out of the brewery outfall pipe. All right, downstream. All right, now we can't just ask this question, does it affect the fish? We have to have something specific that we can measure that's going to tell us how these fish are impacted in order for us to do this experiment at all. And one way to look at how much alcohol the fish are exposed to is to measure an enzyme called alcohol dehydrogenase in the bloodstream. So we have to narrow this question down. So our actual research question is going to be, is this ADH um, higher in the fish downstream than in the fish upstream? So that would be evidence that they're being exposed to high enough levels of alcohol that it affects their physiology. All right, so we have data measurements for our upstream fish. So when we talk about this type of experimental design, this is going to be a 2 independent samples style of t-test. We have individuals that we have sampled that have experienced a certain condition. And then we have a different set completely of individuals that have experienced a different condition. So instead of imposing a condition on them in this example, we could do that as well, but we're collecting them from the environment and a location where they've been exposed to a certain kind of treatment, if you want to think about it. So our upstream fish are like the control, the downstream are the treatment. So this means we can have a different number of individuals in our 2 different samples, right? So it's a 2 sample test because we actually have a sample of individuals, a group of individuals that are completely different. And in order for this test to work, they have to be independent from the individuals that are in our other sample, the downstream sample. Okay, so we have 2 different sample sizes. And we're going to need to calculate the mean of our upstream um, ADH values, and I've used Excel to calculate that. It comes out to be 13.1. And our standard deviation of our upstream values is 10.3. Again, using Excel, same thing with the downstream ADH levels. I took the mean of them. Using Excel, it's 31.9, and the standard deviation is 3.0. Right, and this is kind of a lengthy calculation, and so I'm going to carry this one extra digit in through the calculations. So when we're doing the two independent samples t-test, we have this somewhat longer and more complicated equation. We have to combine the standard deviations of our two samples. And what I've shown you in class, this equation here, is a conservative estimate of the pooled standard deviations that's easy to calculate by hand. So when we use Excel, it's going to use a much more sophisticated equation to find the pooled standard deviation. So when you do this test in Excel, if you did it on exactly the same data, it will come out with a slightly different t-value. But I want you to use this one when you're doing calculations by hand because it's just less cumbersome to work on. Now, the other thing we have to worry about with the two independent samples t-test, if we have different sample sizes, is what do we use for our degrees of freedom? We don't get to add the sample sizes together, but we have to combine the degrees of freedom in some way. All right, so again, a very conservative way to do this that I'm going to have you use when you're doing problems by hand is to just pick the smaller of the sample sizes. All right, so we're going to use the sample size of the upstream sample, and so our degrees of freedom is going to be 8 minus 1, or 7. Again, this is conservative. That means it's going to be harder to reject the null, but we doesn't really matter for our purposes of our practice or homework problems. If you want to actually do a real experiment, you're going to use software to analyze it, so you'll come out with the exact best calculation. All right, so two independent samples, t-test, our null hypothesis is always going to be that the true means of our two different conditions are going to be equal. So let's write some hypotheses. So mu up is equal to mu down. And our alternate hypothesis, so we need to know if we're going to do a one-tailed or a two-tailed. Are we going to have a greater than or a less than, or are we going to have a not equals, right? Our mu zero is always going to be that they are equal. So let's look at our research question, and it asks, is ADH higher in the downstream fish than it is in the upstream? Okay, higher in the downstream. That means we're going to have a greater than symbol in our alternate hypothesis, and this is telling us it's going to be a one-tail p-value. Okay. All right, let's set our alpha level to 0.05. And we'll also look and see what happens if we use a 0.01 just for educational purposes today. All right, now we need to substitute our values into our equation to find our test statistic. I'm going to write out a few of the steps here because getting the order of operations when you're doing the calculation in the denominator here is important. All right, and I'm old school. I grew up using calculators that didn't have any ability to type in parentheses or anything. So I mentally do all the steps one at a time, from the inside of the equation to the outside of the equation. All right. Doesn't really matter which variable we call x1 and x2 as long as we do it consistently throughout. Now notice I've actually labeled my means and my mu's with kind of a code that tells me which of my variables it is. If I just call it x1 and x2, then when I refer back to the research question, it's harder to keep track of exactly what I was asking. So I encourage you to come up with some kind of little a letter code or something to use so that when you're writing out your variables and your hypotheses, that it helps you keep track of what's going on. All right, so we'll call the up x1, and that means we're going to do x bar up is 13.1 minus x bar down 31.9. And then we've got the square root of all of this. All right, so our standard deviation of our number one sample is 10.3. We're going to square that. And then we're going to divide it by the sample size for that sample, which is 8. All right, for this calculation, you need to square 10.3 first and then divide it by 8. Then you can add these two terms together. So when we're adding fractions, if they have the same denominator, we can add the tops together. But if they don't have the same denominator, then we can't add the tops together. And since we're doing these calculations by calculator, I find it easier to just calculate each one of these terms and then add them together without worrying about the fraction. Adding fractions is nobody's favorite thing to do. All right, so we need to put our standard deviation for our second sample in here. This one's 3.0. We're going to square that, and then we're going to write its sample size underneath, which is 9. All right, so on the top, we're going to get negative 18.8. And first, we're going to square these numerator terms, 106.1 over 8 plus 9 over 9. All right, I'm going to keep going step by step. And we've got negative 18.8 in the numerator. And we still need to write this square root in the denominator. All right, so we're going to get 388.3 is, hang on. Sorry, this is not the correct number. It should be 13.3. 9 divided by 9 is 1 plus 1. So I tell you, I don't know how many times I have made these calculations, and it seems like every single time I make some kind of wacky mistake. So like I say, you always need to be constantly vigilant. Anything you calculate now, doing it step by step like this is, you can introduce a lot of mistakes, right? So there's downside to doing it. If you can put this equation into your calculator and get all the parentheses and everything right to make it come out correctly, then that is great. And then remember, if we're really doing this for research, we're not going to make these calculations by hand. We're going to use statistical software. All right. So we're going to get, all right, square root of 14.3 is going to equal 3.8. All right, now remembering to take the square root of this is or forgetting to take the square root is a mistake that a lot of people can make. So our final answer here is going to be negative 4.95. All right, that is our value of t. Remember what we're doing here. And we want to use that to find p. All right, I'm going to remember to share my screen with you to look for our value of our t. So we need to look for the correct degrees of freedom on our t table. And this time we have degrees of freedom, we have 7. So we're going to go to the row for 7. And remember that once we've calculated a value of t, we are going to try and find the value we calculated in our table. Okay, so on the correct row, we're going to go across. We're going to see these numbers that are starting with 1 or 2, and we're going to go across to get 4.029 and 4.785. Oh, ours is even bigger than that. 4.95 is going to be in between 4.785 and 5.408. All right, now we are going to go down to the bottom of the table where it shows our one-sided and our two-sided p-values. In case we forgot, we can look back at our alternate hypothesis, and we made this one a one-tail hypothesis. So we're going to write down those one-sided p-values, 0.001 and 0.0005. I'm going to come back to the scratch paper. Okay, so our value of t, these are t's, 4.95 is in between 4.785 and 5.408. All right, so we're going to convert that to a value of p, an area under the curve in the tail. And remember that as our t's get bigger on the table out to the right, our p's are getting smaller. So you can also examine these values to figure out which way the greater than less than signs should be pointing. But one way to remember is that you flip the direction when you convert from t to p. All right, so we found that our p-value is in between 0.001 and 0.000, that's small 5. All right, so let's look at our alpha levels here. Our next step is to compare our p to our alpha. Is p less than alpha? As always, our next step. And in this case, our p is less than a 0.001. So it is less than our alpha. If our alpha is 0.01, it's also less than our alpha if our alpha is 0.05. So when we have an alpha level that is larger or smaller, occasionally we're going to get a p-value that's in between 0.05 and 0.01. So it actually matters of whether we're going to decide it's significant or not. what our alpha level is. But we want to have in our experiments, we actually, it's much better if there isn't this ambiguity, if we have a quite small p-value. And in fact, when we are looking at some data for most of our statistical tests in Excel, we're going to find that our p-levels are much smaller than that, right? Or we're going to get p-values that are, 1.7 times 10 to the minus fifth or times 10 to the minus 27th, right? So hopefully you don't have an experiment that comes out with a close to significant level. And typically you'd want to redesign your experiment so that you could find a bigger effect size and be really sure. All right, is our p less than our alpha? Yes, yes it is. All right, we need to write our conclusions. So I'm going to go on to the next page where I have some space. So remember our question was, is ADH higher in fish downstream than in fish upstream? In fact, we have found that there is a statistically significantly higher level in fish downstream than upstream. So that's going to look like, oh, we want to make sure we reject our null. That's our next step after is RP less than our alpha. Yes, it is. We're going to reject the null. That means ADH in fish downstream from are statistically significantly downstream is higher than in fish upstream. All right, so that is the result from our little data sampling, our comparison. This is a very specific research question. When we go back to that bigger question of, is there an effect? Does this make the fish drunk all the time? Does this make the fish um, toxic to eat? But we haven't answered any of those questions. All right, we've just found evidence that there is a physiological difference indicating exposure to alcohol in the downstream fish. All right, so when we want to make some kind of bigger conclusion, typically one little hypothesis test like this is not really going to answer a particularly interesting question. And in this case, it might mean that we'd put a temporary warning for people catching fish downstream from the brewery so that they would know that the fish had exposure to alcohol. All right, but we'd need to do a lot more research to figure out what, if any, negative impacts to health of the fish or health of the consumers of the fish might be. And that is your complete answer to question 4.